All right. So as I said before, let's continue exactly where we left off yesterday. So let's take a look at problem 9 from problem set 4, which is the work and energy set. And so this problem is just a quick application of kinetic energy, and then we can move on to the definition of other types of energies. So this problem says an object of mass m equals 0.5 kilograms. Let me make it a bit thinner. Yeah, 0.5 kilograms. Starts moving at initial time t0 equal 10 seconds with an initial speed of 20 meters per second. So v0, that's 20 meters per second. And it says calculate the kinetic energy at t equal 15 seconds. So we want to know kinetic energy at t equal 15 seconds. So it says for question A, it moves with constant velocity. So if this thing is not changing the velocity at all, it will be still 20 meters per second after the mark 15 seconds. So just notice here that the initial time is 10 seconds. So actually the movement that we are analyzing here is happening in a 5-second time span, right? Anyways, for at velocity, the speed, we're just talking about we know it's a straight line. So speed at 15 seconds equals 20 because it's constant, 20 meters per second. So kinetic energy will be, as we define, 1/2 mass v squared. And that's simply 1/2, 0.5 kilograms, 20 meters per second squared. And if you calculate that, you'll get 100 joules. All right. So this is directly applying the definition of kinetic energy that we got yesterday. I trust that you remember the actual origin of this. So we got our equation of motion, and we rewrote the acceleration in terms of the velocity and displacement, and then we replaced that into the we substituted that into Newton's second law, and with that we calculated the work of that force, right? So if you don't remember that, you can always go back to the class, the yesterday's class, and take a look at that. So this thing is not an arbitrary definition. So that 1/2 mv squares, it's coming from an actual derivation. Yes. So that's for A. Velocity is not changing at all, and for B, it says it moves with acceleration of 3 meters per second. Right. So for B, we would need to write our we don't really care how the position is changing, because it's asking about the kinetic energy. So we really care about the velocity at the final instant. So after 5 seconds have elapsed after those initial 10 seconds. So we have acceleration equal 3 meters per second square. sorry, per second squared. So we have final velocity or velocity. Let's use v here. Equal v0 plus acceleration multiplied by t. If you remember that, that's how we, right? So this would be v of t, right? The function of the function that defines the velocity with respect of time. So we have 20 meters per second plus 3 meters per second squared times 5 seconds, right? 5 seconds. Why 5 seconds? Because my initial time is 10 and my final time is 15, right? So I have this 2 here. So actually the movement is taking place in 5 seconds. And then we get 35 meters per second. That's the final speed, and we can calculate it in the same way the kinetic energy as 1/2 of m v squared, and that would be 0.5 kilograms, 35 meters per second squared. And that will give us 306.25 joules. All right, so there it is. We've just applied some kinetic energy definitions here, and we've calculated the amount of the kinetic energy for 2 cases. When the truck is not the object is not accelerating at all, and when the object is accelerating. So of course it will have more kinetic energy if the final speed is higher, and that means that we pumped energy into the system. Actually, we pumped those 206.5 joules extra in order to get more, accelerate the object. Is that clear? Any questions? All right, perfect. Let's move back. If nobody needs the screen anymore, I'll go back to the PowerPoint. All right. Let me stop. And share the class. Can you see it? Because I'm not seeing you with the rectangles with the screens. Okay, thank you. All right. Perfect. Let me pull this aside. And let's continue here. So for today, the idea is to continue with this idea of energy, and we will see 2 more forms of energy, specifically one subgroup, which is the potential energy. So far we've talked about the kinetic energy, so we will take a look at potential energy, and within those 2, the gravitational and the elastic potential energy, and the way energy can be conserved in a system. And this will be the last chapter before our midterm, and it will be it will be included in the midterm. So what I want to do is to finish the class, finish the concepts between today and tomorrow, and for Friday, probably we will, if we have the time, we will go over some fundamental stuff for the exam. Just bear in mind that for the exam, you will have to keep your cameras on. It will be on class time, so from 9 to 10:15, maybe a little longer, in order to finish, and you'll be able to upload your exam to Gradescope. So we will use Gradescope to get your exams. And please, well, I know that you're using it for the discussion, so you shouldn't have a problem with that. But it will be submitted through Gradescope, and the exam you should solve the problems on a sheet of paper, not digitally. So please be prepared for that. You can use pencil or whatever you want to use, pencil, pen, doesn't really matter. The point is that it would need to be readable when you take a picture and upload it to the Gradescope. And another thing, you will need to have your cameras on, just to know that it's you, that you're working there. I'm not asking you to do anything out of what it's normal. Just have your sheet of paper, you can have your calculator, and of course anything to write on that sheet of paper. You cannot use the book or anything, any notes, and I will provide you a formula sheet. So you don't need to, you cannot have anything written, on your own. But yeah, I guess that will be all pretty straightforward. So hopefully we can have the logistics right for the exam without any hassle. Any questions about that, about the exam? Of course, I'll go over this on Friday, but I just wanted to give you like some information, so you're getting prepared for it. All right. There are no questions, then let's continue with the class. Okay, so enable the pointer. Yes. All right, so in this chapter we will see that we can think of energy as something that's being stored and then transformed, from one form to another. So we can transform kinetic energy in some other kind of energy, and we can assess that transfer, and we can explain how the object will be affected by that, how our mobile in this case, our particle for now. So we will prove that in some cases that total energy of the system is conserved during motion, and which are the requisites for that, let's say, and then we will say the law of conservation of energy, which is one of the most fundamental principles of science. Let's put it that way. So that's the importance of it. All right, so let's start with gravitational potential energy. So imagine that you lift an object, right? So you are pulling a force on it. You're applying a force on it to lift it. So there must be some work there, right, in order to get that action. So remember, energy, we can think about it as the capacity of doing work, right? While the force is the actual action, right? The interaction between in this case the object and ourselves. So there is a potential for the gravitational force to do work on an object if I just allow it to fall, right? Because it's embedded, it's submerged in the into the gravitational field, right? So there is an idea of an energy associated with the position of objects in a system. And this position and this energy associated with position is called potential energy, because it's talking about the potential to perform work dependent of the position of that of that particle, of that object. So the specific one, which is associated with an object's weight and height, is called gravitational potential energy, and it's derived from the gravitational field, right? So if we're talking about gravitational potential, we can say, well, this has to be related to gravity, of course, and the force that it's related to, that it's due to gravity, is the weight. So and we know that energy is actually work being performed, the capacity to perform work. So we could think that we can define that we can use the work of the weight to define that potential energy in some fashion, like we did with the kinetic energy, right? Remember that we took the work, we calculated the work of the force that was accelerating the object and changing the velocity. So with the same reasoning, we can do the following. So we have the work of the gravitational force that would be remember when we did that force, when we defined the work in a straight line as just the force multiplied by s, and in this case the force is the weight, so it's mg, right? And the position, the displacement actually is the position 1 minus position 2. Just bear in mind that in this case y1 is bigger than y2, right? So normally we would do y2 minus y1, right? But we would get a minus there, and it would switch the sign, and see that the displacement that we're considering is pointing down, so it's going from top to bottom, right? So we would have, if we substitute the weight, we would have mg y1 minus mg y2, and in this fashion, we can say that this is basically a change in that same quantity, having mg and the coordinate, the y coordinate in our system, and we can define this as the gravitational potential energy associated with that specific particle, which would be mg y, where y is the coordinate, the position, right? And in our system of reference. And of course, you can always define the zero wherever you want to do it. You could define the zero here and have negative positions, and then you have different signs in that energy, but that won't change the physics of it. Remember, changing the system of reference is not changing any of the physics of the problem. So as we said here, so the displacement is downward and y decreases. That's a big distinction here. So y1 is bigger than y2, So the weight does positive work, right? Because it will be taking the object to a lower state of energy. And then the gravitational potential energy is decreasing, right? Because we have that variation, the delta, which is this one here, would be negative, right? Because we are, and it makes sense, right? The object is moving naturally to a position of a lower potential energy. So a better, let's say, a position of equilibrium. So the minimal energy gives us, in general terms, the minimal, let's say, the stable equilibrium state, right? And so we can write this, we can make it more formal as writing the work done by the gravitational force as mgy1 minus mgy2, exactly what we wrote here. And that would be the gravitational potential energy at point 1 minus the one at point 2. So this would be minus delta gravitational potential energy, right? That minus is coming from here, right? Because we have this y, which is bigger than y2, and it makes sense. It will give us a negative sign, right? Any questions about this? So the big takeaway is the definition of the potential energy and how can we relate it to the work of our gravitational force, which is weight. So basically the potential energy is strictly related to the work of the weight in our gravitational field. All right, let's continue. So let's talk about the conservation of the total mechanical energy. So now we will define another, it's another name for it, another quantity, which is the mechanical energy. So for that, let's go back and remember the theorem of work and energy that said that the total work, the work of all the forces acting into an object is the variation of the kinetic energy. We arrived to that statement in the previous class. So if we just suppose that an object's weight is the only force that's acting on it, so this is free falling, nothing is pulling or pushing or doing any other interaction, so we just have the weight, then of course this will be valid, right? And the total work of all the forces, the sum of the work of every force acting, in this case, will be just the work of the weight. So we know that this is equal to delta K. So we know that this is equal to the work of the gravitational force of the weight. And we know from previous slide that this is minus delta gravitational potential energy. So we know this is equal to this, the 0.1 minus the energy at 0.2. And so we can say that delta K would be equal to minus delta gravitational potential energy. Okay, and then we can let's say open those deltas, and we have this, right? And if we rewrite this, we just group one with one, one with one and two with two, meaning that we just do, sum K1 on this side and sum and well, of course, on both sides, right? K1, summing K1 on both sides, we just get rid of this one, and summing the gravitational potential energy 2 on each side, so we get rid of this one, so we can rewrite the whole expression as this. Okay, so here we have the kinetic energy at point 1 plus the potential energy at point 1 equals kinetic energy at point 2 plus the potential energy, gravitational potential energy. So I mean, just let me call it potential energy for the sake of not repeating so much. But yeah, it's gravitational, right? The potential energy at point 2. So we have an expression of the sum of the energies, which is invariant in between that point 1 and point 2. So if only, let's remember, let's not forget our assumption here, right? Our assumption was that the only force acting on it's the weight, right? So if only the gravitational force does work, then the total mechanical energy is conserved. Okay, so this quantity here, kinetic and potential, right? That we are defining it as the total mechanical energy of the system. And we call it with letter E. We use letter E to symbolize that. Is that clear? Any doubts about that? Any questions, concerns? And we can see that we will see that this is pretty useful in when solving problems. So we can say that then that the kinetic energy plus the potential energy is called the total mechanical energy of the system. And in the case that the only force that's acting is the weight, this total mechanical energy will be conserved. It's not changing. Doesn't really matter. The trajectory doesn't matter what the particle is doing. If the work is the only thing that's if the weight is the only thing that's performing work, then this will be conserved over time. So E is constant. That's how we define that. And then we in line with that, we say that a quantity that has always the same value is called a conserved quantity. So we can say that the mechanical energy of the system is being conserved. That's the key word here. So yeah, we just stated an example. So same thing here. Imagine this person just running and jumping. We are not caring about the trajectory, although we know that it's going to be kind of a parabola, right? Because it's like a projectile motion. But when let's just analyze what's happening here. So when the person is jumping, the kinetic energy is decreasing, right? The person has an initial velocity which is decreasing in modulus, because at some point it will need to reach a maximum height and it will stop going up. So it's slowing down as it goes up, right? So the kinetic energy is decreasing, but it's moving into a positive coordinate in our system. Let's say we have the 0 on the ground, so it's going up. So it's increasing its position in the y-axis, right? So it will have a mg times y, even bigger from if we compare it to the ground, because y would be 0. So the potential energy will increase at this point, right? And it will be maximum for this this whole motion, and we can write the mechanical energy as the sum of those two. So when we are at this point, the lowest point, we have kinetic energy, let's say maximum, and we have the potential energy at minimum. And then when we get to the top part, then we would have kinetic energy minimum, not 0, minimum, because if it's 0, then the person won't be able to continue, right? It must have some something there, some velocity on the x-axis, and the potential energy will be maximum, right? Because it will be the highest point. And when it moves down, k increases because we know that the person will be being accelerated by the gravity, and the speed will increase, the velocity, the velocity vector will point somewhat like in this direction, and we will get an increase in kinetic energy, and the gravitational potential energy will decrease because it's going down. It's going from a high, let's say a y coordinate, which a high y coordinate, to a lower y coordinate, which is 0 actually in the end, and it will decrease. So if we write the mechanical energy of the system, it will be the sum of those two, and that will be conserved over time. All right, so that mechanical energy is not changing. And if you think it really quick, the velocity of the person in this spot after it touches the ground should be the same, the same as the velocity that it just in modulus, right? Not in direction, should be the same as the velocity that it used to jump, right? Because the kinetic energy should be the same, right? Because now we don't have any potential gravitational potential energy at the final point, the final position, right? So it's like a relationship between two bars. One goes down, the other goes up, and then the other goes down, and then the other goes up. And at some point, I don't know, some point in the middle, somewhere or here, they will have the same quantity, right? Because this E is keeping its value all over the motion. All right, that concept is quite useful, and please save it into your memory, and it will come handy when we talk about other kinds of energy, specifically the elastic energy. Okay, let's move on here. So now let's just generalize this result. So we've just seen we just defined this whole thing for a straight line, and we will see that if we apply the same reasoning to a curved trajectory, curved path, then we will arrive to the same expression, and the result won't change at all, meaning that the gravitational potential energy is it's not dependent of the trajectory that the object is following. It's just dependent of the y coordinate, meaning that we have lines of equal potential, right, over our system. So if we want to make it more formal, we can take the definition of the work of the weight. So let's just not confuse this. This is weight. The W with the arrow is for weight, right? And this is the work, right? So work is cap W, and this one is just for the weight. So that's mg, right? So we are taking the dot product between the force and the displacement, and that's how we define actually the work, right? Remember when we did the integral of that. So we can write the components in terms of the unity vectors. So we have the vector j. So they're not graphs. They're not in the graphic, but you know that the unity vector j points to the it's parallel to the y direction, and the unity vector I is parallel to the x direction. So we can have this, the displacement in terms of those projections of the displacement into the coordinate system, and you can see that we have only a component that's on the y-axis. So this will give us just a component on the y-axis, meaning that the work of the weight is not caring at all about the displacement on the x-axis. So if we continue doing this and we rewrite the delta y as y2 minus y1, so we have the top the lower position minus the top position. This is smaller than y1 here, and we will get a minus sign there that will give us the same result as before. So, I mean, this is the same reasoning as before, but just taking into account some motion on the x-axis, and of course it's invariant in terms of the x coordinate. So the fact that the particle is moving on the trajectory that you prefer doesn't really matter. It doesn't need to be just a free fall. It could be doing whatever, but the work of the weight won't be dependent of that. It will just depend on the y coordinates. So you can think as having, lines, like let's say we have 0 potential energy here, then we have some other potential energy here. But the whole line doesn't really matter where you're standing over that line, just matters where you are at the y-axis. All right, and that's a pretty interesting result actually, and it's it's due to the fact that the weight, it's always pointing down, right? Because that it only cares about the projection of the force of the force which is parallel to the projection of the displacement into that axis, right? So this is basically what we're seeing here, right? So if you remember that definition of modulus by, the definition of the dot product, right? Where you have the modulus of both vectors and the cosine of the angle that they form. So basically we were projecting one vector into the other, right? And this is why for this particular case, as mg, as the weight is always pointing down due to the nature of that force, then we can say that it doesn't really care about the position on the x-axis. Okay. Is that clear? Are we good with potential energy? Any questions? Let me see. Yeah, we can take a look at a problem of potential energy. Let's see. If there are no questions at all, I'll just move to the board, and then just stop sharing this one. So are we good? No questions? Questions or concerns? All right. Let me stop this. And let me enable. Take a look at problem 14. Yes. Problem 14, same set, work and energy. And let me read it. So it says, calculate the kinetic energy of an object weighing 45 newtons dropped from the edge of a 300-meter high building when it is 15 meters above the ground? How does its speed depend on its height if air resistance is neglected? Right. So let's get to that. So we have, let's say we establish our system with the y-axis pointing up. So we have 2 points. We have H, B, H, A, right? Two different heights. And we have, let's just draw the building if you want. We have the ground here. Point B, and we have point A here. And it says that the weight is 45 newtons. It says that P is at 300 meters and A is 15 meters. Okay, and we need to calculate the speed, right? The terminal speed. And I mean, this is a free fall, right? So we'll see another way to calculate the velocity without thinking about the equations of motion, right? So we are not interested in getting the particle at every, in getting the trajectory of the particle, or even the way the position is varying over time. We just care about the final speed at that instant when it traverses point A, which is 15 meters above the ground. And for that we can actually use the energy. Where can energy approach? So we know that in this case, the only force that's acting on the what is that? It's an object. It's not even a ball or a stone. It's just object. So the only force that's acting on that object, it's the weight, right? So we just have the weight, which is mg. We know that, and the weight will be pointing towards the end, the ground, and then we can take a look at what's happening with the energy, the mechanical energy at those 2 points, A and B. So let's start with the start of the movement. So I call it B. You can call it whatever you like. It could be A and B. Switch those letters. But let's say in B, we have the potential. Let me do this. UP, the potential energy, gravitational. We're always talking gravitational now. You know what? Let's do this. So U, it's always potential energy, right? So UG, gravitational. That's mg h b. Okay, that's what we just defined. So that's the energy that we have at point B. We're just taking the coordinate, multiplying it by mg. And for the kinetic energy at point B, we would have nothing, 0, right? Because let me just write the whole thing. Oh, okay. Um, I don't know if you're hearing that, but there is an alarm sounding in the building. Um, Let me just pause a second, guys. So the alarm is still going. I don't know. Can you tell me if you can hear me? If not, I'll just mute and I'll continue with the problem without talking. But you're not hearing the background, right? Oh, okay, that's awesome. So that means that the headphones are blocking it, right? Okay. Sorry if you get something in the middle, but okay, let's just continue with this. Um, all right, so we had kinetic energy, so we have 1/2 m v and b squared, and that will be 0. Okay, so so we have potential energy for point B, and we have kinetic energy equals 0 for point B. And then if we take a look at A, oh yeah, let's just define, the total mechanical energy of point B would be UG plus K. And in this case, there will be just mg HB, right? And we know that this should be constant because uh, there's nothing else acting here but the weight. And then we can take a look at B, at A, sorry. And in A, we have the potential energy HK, which is um which is not 0, because remember this thing is asking for the object at point y equal 15 meters, so it's not 0. And then we have K equal to 1/2 mVA squared, right? And we know that that can be 0, right? Because the object falling has accelerated going down, and due to gravity, and and um and you get some final velocity there. So um so what we can do here is um basically uh equalize. If we do a if we do EA, so the total energy would be GHA, sorry, this is image, plus 1/2 mVA squared, right? And as those two are conserved, so we have these two, and probably 1, 2. We know that 1 equals 2 for the whole movement. And then we can write that mgh a plus 1/2 mva squared equals mghb, right? And from this, we can get, mgha to the other side, and it will be, we can subtract that, and we will get 1/2 mva squared equal mghb minus ha. And basically, this will give us, right, this is kinetic energy, and that kinetic energy is what we actually need, right? So we can calculate that. Oh, okay. I don't know if you were hearing it while I was talking, but it just stopped. So hopefully the building is not on fire. But normally these alarms are not a big deal, but you need to always check, right? But okay. Now I can hear myself thinking. Cool. So now we can just get the numbers there. So we have 45 newtons, 300 meters minus 15 meters, and that will give us the kinetic energy, which is 12,825 joules. All right, let me just write this. So this is kinetic energy at point 8. And that's one of the questions, if I'm not wrong. Yeah, the kinetic energy. And now we can calculate the the speed, the velocity, right? Because we know that. But let me get a let me get an expression of that, because it says how does its speed depend on its height, right? It's not asking for the number. It's not asking for a value for the final velocity. It's asking the dependence with the y coordinate, right? So you can, this would be for question part A, let's say, and this would be part B, although there are no letters there, but just to be more organized. And we can write mg hb equals mg ha plus 1/2 mva squared, right? We have that's when we equalized 1 and 2. So what can we do here? Get rid of m. We have it everywhere. And then we can rewrite this in order to get the velocity at A, which is equal to 2g, oh, sorry, 2g hb minus ha. And we have the square root of that. So that's the expression that's relating the final speed with the variation of the y coordinate. So this is delta y basically. All right. So pretty useful in terms of practicity, because imagine that the thing is not just free falling. Imagine that this thing, I'm just telling you that it's following a, you know, just random path between A and B. So it's not going, sorry, B and A, from B to A on a straight line, free falling. It's just taking, I don't know, some kind of, roller coaster thing, doing something like this, and then arriving to A, right? So the velocity will be the same. Speed for A would be the same. It's not changing at all. If, only if, the only force that's taking part here is the weight, right? So if we have weight, it doesn't really matter the trajectory that the particle is following. So we wouldn't be able to take a look at this. We wouldn't be able to solve this with our equations of motion, right? But we are able to solve it with energy. Any questions about this? Let me center it. No questions? Is that it's all clear? All right. That's pretty good, actually. Yes. Very nice. And let me go back to the PowerPoint to find the elastic potential energy, and we will be done for the day. All right. So this definition of the elastic potential energy, what we just talked about was the possibility to assess whether the gravitational field was, like being able to would let us to store, right, some energy in different coordinates of our system. Basically, that's the main, idea, the main intuition in here. So so this is kind of a same reasoning in terms of storing energy in a deformable object, such a spring or a rubber. And this would be done in terms of the elastic potential energy. So as we said before, the potential energy is it's being defined by the coordinate that the object is occupying in space. So the elastic potential energy would be related to some, as you can assume, some elastic force, right? So if you remember, if you can recall, we took a look at Hooke's law, and Hooke's law was defining the way a spring or something that has a restoring force behaves, right? And that force was dependent of the position. So an object is called elastic if it returns to its original shape and size after being deformed. Let's just think about a spring, right, or a rubber band. So we'll consider we'll always consider an ideal spring. So that ideal spring won't have any mass, right? So it will be massless. Just like the when we talked about ideal ropes, right? Or ideal strings, they don't have mass, but those were not stretching. So this one is stretching. And the force that it will exert, in order to go back to the original shape, to the resting position, will be equal to a constant multiplied by the coordinate in which the spring is is actually. So there's a linear relationship between the force, the elastic force, and the position of the spring. And I'm just refreshing that concept. That was Hooke's law that we reviewed last week. So let's go to some graph here, and we can get this idea into place. So let's think about a spring. We have a block attached to the end of that spring, so it's not compressed and neither stretched. Neither stretched nor compressed. So we have x equals 0. That's the resting point of our spring. And then if we start pulling it, let's say we pull it from x1 to x2, we have a displacement for that object, and we have a displacement vector here. And what can we do? We can calculate the work, right, of that force, which is trying to pull the spring to the resting position at our origin in our system. And just bear in mind that this F is pointing on the opposite way of the displacement, right? So that would have a negative impact in the work. So let's take a look at this. The work we must do on the spring, the one that we are doing, to move one end from x1 to x2 is basically this, right? If we calculate that, remember the force was k times x. So if we integrate that and we get the work done by the force between those 2 points, we get 1/2 x, 1/2 kx squared, right? And just evaluate that function in the point 2 and point 1. But the work done by the spring, it's the opposite, right? It's the work that it has to be done in order to go from x1 to x2. This is a matter of when we're pumping energy into the system and when the system is trying to go to a minimum state of energy. So the spring is trying to go back to a minimum state of energy, which is the resting position at 0. So as the spring relaxes, it does. Well, let's just finish with this example here. So as the spring stretches, it does negative work on the block, right? It's trying to go back to a resting state. It's pulling energy from the system, and as the spring relaxes, it does positive work, right? Because it's going to the resting position. So it will look for that resting point. And if we take a look at what happens in the other two, when we cross that frontier there, the origin, then we would have the same idea, right? The compressed spring also does positive work on the block as it relaxes. So we always have positive work when the spring it's pulling towards that origin. Okay. Right. So if we take a look at the work that the spring is that the elastic force basically is performing, then you can notice that we have, similarly to the potential gravitational potential energy, we have an expression which is stating the difference of two states in our system of coordinates, so state 1 and state 2. So we can define that quantity as 1/2 kx as something that will be assuming different values in terms of coordinates. So we can rewrite that as the elastic potential energy. right? It's the same reasoning that we applied before. So that would be 1/2 of k. That's the constant of the spring, and then we have the elongation of the spring, right? Which is positive if it's stretched, and which is negative if it's compressed. But this thing is it's elevated to the second power, so it's squared, and that sign won't change the sign of the elastic potential energy. So that's related to what we just seen. The spring is always trying to get back to the rest position. And similarly to before, we can write that the work of the elastic force will be minus the variation of the elastic potential energy, and of course, the more the spring is compressed or stretched, the greater its elastic potential energy. So we can think about storing that energy while we are compressing it. And if we get if we graph that elastic potential energy versus the position, then you can see that this is a quadratic expression without, there are no other terms. There is no linear term or independent term here. So this will be a parabola centered into, in the y-axis, and the minimum value of that parabola will be 0. And it makes sense. We will have zero elastic potential energy when the spring is not stretched nor compressed, right? So similar, but not the same as the gravitational potential energy. And we can apply the same reasoning as before. If we have the work energy theorem, which is saying that the total work of all the forces in our object will be equal to the variation of the kinetic energy. And so in this case, if the only force that's doing work for our system is the potential elastic, the elastic force, so we will have just the work of the elastic force, and that will be just a second, guys. I'm having someone knocking at the door. Just a second. Yeah, they are checking the fire alarms. So sorry about that. So this is the last slide. So let's just finish with this. So I was saying that we have the work of the elastic force, which is the only force that's acting. Actually, not the only force that's acting. It's the only force that's doing work. Because of course we can have the weight, right? Remember, if the weight is just pointing down and we are moving on a horizontal line, then the work won't be performing any, the weight won't be performing any work, right? Remember that? So it doesn't really mean that it's the only force that's acting. It could be another forces that are not performing work, right? So the elastic force is the only force that's performing work, and that we just define it as the elastic force at point 1 minus the elastic energy at point 1 and the elastic energy at point 2. And we can apply the same reasoning as before if we just equalize these two expressions. So we have the work of the elastic force equal to the variation of the kinetic energy, and then we can equalize this to the variation of the kinetic energy, and then we have this nice expression down here where we can group what's happening at point 1 with point 1 and point 2 with point 2. So we have the kinetic energy, we have the potential energy equal to the kinetic energy at point 2, and the potential energy at point 2. So in the case that we don't have any any intrusion by the gravitational potential energy, then we just have elastic potential energy, and we can define in the exact same way the mechanical energy of the system as the sum of the kinetic and the potential. So conceptually speaking, this is the same reasoning as before, just taking into account the work of a different force, which is the elastic force, a restoring force, as it's known. All right. Any questions about this particular potential energy, the elastic one? Okay, that's good. Oh, where did the formula for elastic potential energy come from? Look like? Oh, yeah, let me go back. So this thing here, so you have the force here, right? So which is K multiplied by X. That's perfectly, that's exactly what you're saying there. So the elastic potential energy is coming from calculating the work of that force. So if you need to calculate the work, remember that in order to do that, you would need to integrate the dot product between the force and the differential of the displacement. You know, that comes from the definition of work. So when you integrate that, K multiplied by X, integrated, the X integrated between two extremes, then that K is a constant, which comes out of the integral, and X integrated with dx would give us x squared divided by 2, right? Because when you have x squared, you get the derivative of that, you get 2x. So you need that 2 at the bottom to cancel the 2 and then get that back. So you get something like this, Nathan. You get this when you're calculating the work. And basically we define, okay, awesome. Any other questions? All right. If there are no questions, sorry for the interruptions with the fire alarm, but this thing happens. So I'll just see you all. I'll just see you all tomorrow, and then we can finish wrapping this whole thing. We can finish the chapter, and we can prepare for the final thing.